Our Sun is 1,000,000 times the volume of Earth, and these stars make the Sun look like a grain of sand on an endless beach. For over a century, astronomers have been scanning the sky with one impossible question hanging over their heads: how big can a star actually get? Not theoretically, not in some computer model, but out there burning in the real universe, obeying the same laws of physics we think we understand. And the answer they've found is so extreme, so far beyond what most people imagine when they picture a star, that it breaks the sense of scale you've been carrying around your entire life. There is a star out there right now, so enormous that if you replaced our Sun with it, its surface would reach past Saturn, past the rings, past the orbit of the gas giants we've known since childhood. A sphere of fire so vast that light itself takes hours to travel around it. And here's the strangest part: we almost never found it. It sat there for decades, hidden in a distant star cluster, ignored, misclassified, dismissed as unimportant, until a handful of astronomers finally looked at the data closely enough to realize what they were seeing. This is not science fiction. This is the edge of observable reality, the place where stars stop behaving like the neat, tidy objects we learned about in school and start becoming something else entirely. Something that challenges every assumption about how matter, gravity, and fusion are supposed to work. So how does a star grow this large? What separates an ordinary sun from a hypergiant that dwarfs everything around it? And why, in an age when we can measure galaxies billions of light years away, did it take us this long to find the biggest star in our own galaxy? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. Our Sun is enormous. That's the impression most of us carry around without thinking too hard about it. And by human standards, that impression is absolutely correct. You could line up 109 Earths side by side across the Sun's diameter and still have room left over for a few more continents. The thing is 864,000 miles wide. If you somehow hollowed it out like a cosmic jack-o'-lantern, you could stuff roughly 3 million Earths inside the empty shell before you ran out of space. That's not a metaphor, that's geometry. 3 million planets the size of ours fitting inside a single star. The mass is even more absurd. The Sun contains 86% of all the mass in the solar system. Everything else, Jupiter, Saturn, all the other planets, every moon, every asteroid, every comet drifting through the Kuiper belt, all of it combined barely registers as a rounding error. If you weighed the entire solar system on a cosmic scale, the Sun would account for 998 out of every 1,000 pounds. The planets wouldn't even move the needle. And it's not a solid object. It's a ball of superheated gas, mostly hydrogen and helium, held together by its own gravity and powered by nuclear fusion happening deep in its core. The surface temperature sits around 10,000 degrees Fahrenheit, hot enough to vaporize any known substance in less time than it takes you to blink. The core, where hydrogen atoms are being crushed together into helium under pressures we can barely simulate in a lab, runs at about 27 million degrees. That's not an estimate. That's a measurement derived from decades of observation and confirmed by the particles streaming out of the Sun's interior at nearly the speed of light. For all practical purposes, standing on Earth and looking up at the sky, the Sun is the definition of massive. It dominates our experience of the cosmos. It provides all the heat, all the light, all the energy that makes life on this planet possible. Without it, Earth would be a frozen rock drifting through the void at -400 degrees, lifeless, silent, and invisible. So yes, the Sun is big, except when you start comparing it to other stars. The Sun stops being big and starts being embarrassingly average. And once you meet the real giants of the stellar neighborhood, the Sun doesn't just shrink, it vanishes. Astronomers classify stars by their size, temperature, and luminosity. Our Sun falls into a category called G-type main sequence stars, also known as yellow dwarfs. The name is a bit misleading because yellow dwarfs aren't actually yellow, they emit white light, and they're not exactly dwarfs either, at least not compared to the smallest stars in the universe. But in the grand taxonomy of stellar objects, the label stuck. A yellow dwarf is a star in the middle of its life, burning hydrogen in its core, stable, predictable, and thoroughly unremarkable. Main sequence stars, the category our Sun belongs to, range in size from about 1/10 the Sun's diameter to roughly 10 times larger. Red dwarfs sit at the small end. They're dim, cool, and incredibly long-lived. Some of them will burn for trillions of years, far longer than the current age of the universe. At the other end, you have massive blue stars that burn so hot and so fast they exhaust their fuel in a few million years before exploding as supernovae. The Sun sits comfortably in the middle, not too hot, not too cool, not too big, not too small. It's been fusing hydrogen into helium for about 4-6 billion years, and it has enough fuel left to keep doing that for another 5 billion or so. Eventually, it will swell into a red giant, swallow Mercury and Venus and possibly Earth, then collapse into a white dwarf and fade into darkness over trillions of years. Standard stellar evolution, nothing unusual, but main sequence stars are only part of the story. Once a star exhausts the hydrogen in its core, it leaves the main sequence and enters a new phase of life. What happens next depends almost entirely on how massive the star was to begin with. Low-mass stars like the Sun puff up into red giants, shed their outer layers and die quietly. High-mass stars do something far more dramatic. They swell into red supergiants. This is where the scale starts to break. A red supergiant is a star that has burned through the hydrogen in its core and moved on to fusing helium, then carbon, then heavier and heavier elements in a desperate attempt to stay alive. The outer layers of the star expand outward, sometimes by hundreds of millions of miles, while the core contracts and heats up. The result is a star with a relatively cool surface temperature, which gives it a reddish hue, but an absolutely enormous physical size. Some red supergiants are 25 times wider than the Sun, others are 100 times wider, a few are more than 1,000 times wider. If you placed one of these stars where the Sun is right now, its surface would extend past the orbit of Mars, in some cases past the orbit of Jupiter. You would not see it as a distant point of light in the sky. You would be inside it. And then there are the hypergiants. These are stars so massive and so bloated that they sit at the absolute edge of what stellar physics allows. They burn through their fuel at a catastrophic rate, losing mass in violent stellar winds, flickering and pulsating as their outer layers struggle to stay bound to the core. Most hypergiants don't last more than a few million years before they explode or collapse. They are not stable. They are not predictable. They are cosmic accidents, burning as bright as entire galaxies for a geological blink of an eye before vanishing forever. The largest hypergiant ever measured is roughly 1,420 times wider than the Sun. Think about that number for a second. Not 10 times wider, not 100 times wider, nearly 1,500 times wider. If you replaced the Sun with this star, light would take more than 8 hours to travel from one side of its surface to the other. Light, the fastest thing in the universe, 8 hours to cross a single star. For context, light takes about 8 minutes to travel from the Sun to Earth. That's 93 million miles. The distance from the Sun to Jupiter, the largest planet in the solar system, is about 484 million miles. Light covers that in roughly 43 minutes. The distance from the Sun to Neptune, the outermost planet, is about 2.8 billion miles. Light takes a little over 4 hours to get there. A hypergiant 1,420 times the diameter of the Sun would have a radius stretching well beyond the orbit of Jupiter. Its surface would be closer to Saturn. If you stood on Earth and somehow the Sun were instantly replaced with one of these monsters, you would not see a sun in the sky. You would see the sky itself glowing. The entire horizon, from every direction, would be filled with the dim red surface of a dying star. There would be no night. There would be no day in the way we understand it. Just a faint, unchanging twilight as the star's outer atmosphere drifted past the planet at thousands of miles per hour, stripping away the atmosphere, boiling the oceans, and incinerating the surface. But let's not get ahead of ourselves. We're still standing in our own solar system, still looking up at our average-sized Sun, still trying to wrap our heads around the idea that somewhere out there stars exist that make our Sun look like a grain of sand on a beach. To understand just how small the Sun really is in cosmic terms, you need to understand how astronomers measure stellar size. You can't just point a telescope at a distant star and see how wide it is. Even with the most powerful instruments we have, stars are so far away that they appear as single points of light. The only star we can actually resolve as a disk is the Sun, and that's only because we're sitting right next to it. Instead, astronomers use a combination of techniques. They measure the star's brightness, its temperature, and its distance. From those three pieces of information, they can calculate how large the star must be to produce the light we're detecting. If a star is incredibly bright but relatively cool, it must be enormous to compensate. A cool surface doesn't emit much energy per square meter, so the only way to produce that much total light is to have a truly massive surface area. They also use a method called interferometry, where multiple telescopes work together to simulate a single gigantic telescope with a much larger effective diameter. This allows astronomers to measure the angular size of the largest nearby stars directly. The results have been consistent across different methods. The biggest stars really are as big as the math suggests, and the numbers are hard to believe even when you see them written down. Take Arcturus, a red giant located about 37 light-years from Earth. It's one of the brightest stars in the night sky, visible from almost anywhere on the planet. Arcturus is about 25 times wider than the Sun, not 25% wider. 25 times. If you placed it where the Sun is, its surface would extend halfway to the orbit of Mercury. Or take Sirius, the brightest star in Earth's night sky. Sirius is actually a binary system, two stars orbiting each other. The primary star, Sirius A, is about 1.7 times the diameter of the Sun and roughly twice as massive. It's hotter, brighter, and younger. By most measures, Sirius A is a more impressive star than our Sun, and it's still tiny compared to what's out there. The Sun's diameter is 864,000 miles. Multiply that by 25 and you get Arcturus. Multiply it by 100 and you start approaching the size of the largest red supergiants. Multiply it by 1,000 and you're in hypergiant territory, where the rules of stellar structure start bending under the sheer scale of what's happening. At that size, a star's gravity can barely hold itself together. The outer layers are so far from the core that they drift away into space, carried off by radiation pressure and stellar winds. The core is frantically fusing heavier and heavier elements, trying to generate enough outward pressure to keep the star from collapsing. And the whole structure is pulsating, expanding and contracting over periods of months or years as the star struggles to find equilibrium between the inward pull of gravity and the outward push of fusion. These stars are not stable, they are dying. And they are doing it on a scale that makes our sun look like a candle flame next to a forest fire. NASA's educational resources like to point out that the sun is average. They're not being modest, they're being precise. In a galaxy containing somewhere between 100 and 400 billion stars, the sun sits almost exactly in the middle of the pack, in terms of size, temperature and lifespan. There are stars far smaller. There are stars far larger. And the largest ones, the true cosmic behemoths, are so far beyond the sun in scale that comparing them feels less like astronomy and more like mythology. But they're real, and we've found them, not by accident, not by luck, but by methodically mapping the sky, measuring the light from distant stars, and calculating just how big something has to be to shine that bright from that far away. The sun contains 86% of the mass in our solar system. It dominates everything within billions of miles. It is the reason we exist, and in the larger universe, it is a speck of dust, a dim, ordinary middle-aged star in an unremarkable spiral arm of an average galaxy. There are stars out there, right now, that would swallow our entire solar system and still have room left over. Stars so large that if you tried to fly past them at the speed of light, it would take you the better part of a day just to clear the diameter. Stars that burn brighter than entire galaxies, visible across distances so vast that their light takes millions of years to reach us, and we're about to meet them. One by one, starting with a star you can see with your own eyes on a clear autumn night, glowing faintly red in the constellation Cephei, a star that makes the sun look small, a star that was recognized as extraordinary more than 2 centuries ago, a star that earned a name that still fits, the Garnet Star. The Garnet Star, Mu Cephei's fiery embrace. We're standing at the edge of something now. The sun behind us, shrinking in the rearview mirror of cosmic scale, and ahead of us, the first true giant, a star that has been sitting in the night sky for as long as humans have looked up, glowing faintly red in a constellation most people have never heard of, waiting patiently to be noticed. It took until the 1780s for someone to really see it. That someone was William Herschel, the man who discovered Uranus, mapped the Milky Way, and spent his nights obsessively cataloguing everything in the sky that didn't move like a planet or blink like a comet. Herschel was a musician by training, a composer and oboist, who taught himself astronomy in his spare time and built his own telescopes because he couldn't afford to buy one. By the time he pointed his homemade instrument at the constellation Cephei, he had already discovered more objects than most professional astronomers of his era. He was good at noticing things other people missed. What he found in Cephei was a star that glowed a deep, vivid red, not the pale orange of Arcturus, not the yellowish tint of Betelgeuse when it dims. A rich, saturated garnet red, the color of a gemstone held up to candlelight. Herschel was so struck by the color that he wrote about it specifically, calling it one of the most beautiful stars he had ever observed. The name stuck. Astronomers still call it the Garnet Star. More than 2 centuries later, even though its official designation is Mu Cephei, the 12th brightest star in the constellation by traditional ranking. Cephei itself is not a well-known constellation. It's a circumpolar pattern, meaning it never sets below the horizon if you're watching from the northern hemisphere, but it's also faint and awkwardly shaped, sitting near Cassiopeia and Draco in a relatively empty patch of sky. You need a clear night and patience to pick it out. Mu Cephei sits near the edge of a large nebula called IC 1396, a region of glowing gas and dark dust clouds where new stars are being born. The Garnet Star itself is not being born, it's dying, and it's doing it on a scale that makes the sun look like a birthday candle. The first thing you notice if you manage to find Mu Cephei in the sky is that it's not always the same brightness. Sometimes it glows at magnitude 3, 4, bright enough to see easily with the naked eye even from a moderately light-polluted city. Other times it fades to magnitude 5, 1, right at the edge of visibility, requiring dark skies and a bit of effort to locate. This variability is not random. The star pulses on a semi-regular cycle, brightening and dimming over a period of about 860 days, roughly 2.5 years. The pulsation is driven by instabilities deep inside the star's structure, where the outer layers expand and contract as the core struggles to maintain equilibrium. It's a symptom of a star that has lost control of its own physics. The color is the second thing you notice, and it's what makes Mu Cephei memorable, even if you've never looked at it through a telescope. Most stars appear white or pale yellow to the naked eye. The human retina isn't great at detecting color in faint light, so unless a star is unusually bright or unusually red, your brain averages it out to something neutral. Mu Cephei is red enough to override that. If you find it on a clear autumn night and stare at it for a few seconds, the garnet hue becomes unmistakable. Herschel wasn't exaggerating. The star really does look like a gemstone floating in the dark. That color is telling you something important. It's telling you the star's surface is cool, at least by stellar standards. Mu Cephei's effective temperature sits somewhere between 3,551 and 3,750 Kelvin. For comparison, the sun's surface is about 5,778 Kelvin. The difference sounds small, but in stellar physics, a couple thousand degrees changes everything. A cooler surface radiates most of its energy in the infrared, shifting the visible light it does emit toward the red end of the spectrum. The result is a star that glows like a dying ember, faint in visible light but extraordinarily bright when you account for the infrared radiation pouring off its surface. And then there's the size. This is where Mu Cephei stops being interesting and starts being incomprehensible. The star's radius has been measured using multiple techniques, including interferometry, spectroscopy, and brightness modeling. The estimates vary depending on which study you trust, but the consensus range falls between 1,000 and 1,650 times the radius of the Sun. Most sources cite a value around 1,260 to 1,500 solar radii as the best estimate. Let's use 1,500 for simplicity. If you replaced the Sun with Mu Cephei, the star's surface would extend past the orbit of Mars. Some estimates place it near the orbit of Jupiter. You would not be looking up at a star in the sky. You would be inside it, drifting through the outermost layers of its bloated atmosphere as the planet slowly spiraled inward toward the core. Mars orbits the Sun at an average distance of about 142 million miles. Jupiter orbits at 484 million miles. If Mu Cephei's radius is 1,500 times the Sun's, that translates to roughly 648 million miles across the diameter. Light traveling at 186,000 miles per second would take about 58 minutes to cross from one side of the star to the other. You could fit 26 billion Earths inside the volume of Mu Cephei before you ran out of space. That number doesn't mean much until you try to visualize it. Imagine taking Earth, the entire planet, and shrinking it down to the size of a marble. Then imagine filling a sphere the size of Mu Cephei with those marbles, packed edge to edge with no gaps. You would need 26 billion of them. That's more marbles than there are people on Earth. That's more marbles than the number of seconds in 40 years. And each one of those marbles is a planet the size of the one you're standing on right now. The luminosity is just as absurd, depending on which study you cite. Mu Cephei radiates somewhere between 100,000 and 269,000 times more energy than the Sun. The range is wide because calculating the luminosity of a distant, variable, heavily obscured star is not straightforward. The star is surrounded by a thick shell of dust created by its own stellar winds, and that dust absorbs a lot of the visible light and re-radiates it in the infrared. You have to account for the dust, correct for the distance, factor in the pulsations, and make assumptions about the star's mass and composition. Every assumption introduces uncertainty, but even the low end of the estimate is staggering. 100,000 times the Sun's luminosity means Mu Cephei is pumping out as much energy in 1 second as the Sun produces in 27 hours. The high end of the estimate makes it nearly 3 times brighter. The distance to Mu Cephei is another source of uncertainty, and it matters because distance affects everything else we calculate. Early estimates placed the star at around 2,090 light-years from Earth. More recent measurements using parallax data from the Gaia satellite push the distance closer to 6,000 light-years. If the star is farther away, it must be intrinsically brighter to appear as bright as it does from Earth, which means the luminosity estimate goes up. It also means the star is physically larger than we thought. The current best guess seems to hover around 2,500 to 3,000 light-years, though the error bars are still uncomfortably wide. What we do know with more confidence is how this star ended up like this. Mu Cephei started its life as a high-mass star, probably somewhere around 19 times the mass of the Sun. That's big. Not the biggest star that can form, but well above the threshold where you stop worrying about living a long, boring life and start burning through your fuel at a catastrophic rate. A star that massive spends only about 10 million years on the main sequence, fusing hydrogen into helium in its core. For comparison, the Sun has been on the main sequence for 6 billion years and has another 5 billion to go. Mu Cephei burned through its hydrogen budget in less time than it takes for a mountain range on Earth to erode. When the hydrogen in the core ran out, the core contracted and heated up, igniting a shell of hydrogen burning around the inert helium core. The outer layers of the star, no longer supported by the pressure from core fusion, began to expand. The star left the main sequence and became a red giant. Then it ignited helium fusion in the core, fusing helium into carbon and oxygen. That phase doesn't last long either, maybe 1 million years. Then the helium runs out, the core contracts again, and the star enters the final act. It's now fusing carbon in the core, or possibly oxygen, and the outer layers have expanded so far that the star has become a red supergiant or a red hypergiant, depending on how you classify it. Mu Cephei is losing mass at a ferocious rate. Current estimates put the mass loss at around 1/10,000,000th of a solar mass per year. That might sound small, but over the course of a few thousand years, it adds up. The star has already shed enough material to create a thick dust shell extending roughly 15,000 astronomical units from the core. That's about 375 times the distance from the Sun to Pluto. The dust is expanding outward at roughly 10 kilometers per second, pushed by radiation pressure and stellar winds. The shell is probably between 2,000 and 5,000 years old, meaning it was ejected sometime around the time the ancient Egyptians were building the pyramids or the ancient Greeks were just starting to write down their myths. There's also evidence of a mole sphere, a region of the star's outer atmosphere where water vapor molecules are present in surprising quantities. This shouldn't be possible in a star this hot, but the outer layers of a red supergiant are so diffuse and so cool that chemistry starts behaving more like chemistry on a planet than chemistry in a star. Water vapor, titanium oxide, carbon monoxide, all kinds of complex molecules form and survive in these extended atmospheres before being blown away into space. The star is not stable. It can't be. The outer layers are barely bound to the core. Gravity is still holding the star together, but only just. The radiation pressure from the core is pushing outward. The stellar winds are stripping away the surface, and the pulsations are shaking the entire structure every few years. At some point, probably within the next few 100,000 years, Cephei will reach the end of its fuel supply. The core will begin fusing heavier and heavier elements, working its way up the periodic table, from carbon to oxygen to neon to magnesium to silicon and finally to iron. Each stage releases less energy than the one before, and each stage happens faster. The final stages from silicon to iron take only a few days. Iron is where fusion stops being profitable. Fusing iron into heavier elements doesn't release energy, it absorbs it. Once the core fills with iron, there's no more fuel left, no more outward pressure, nothing to hold the star up against its own gravity. The core collapses in less than a second. Protons and electrons are crushed together, merging into neutrons. The collapse halts when the core reaches neutron degeneracy pressure, the point where quantum mechanics says the neutrons physically cannot be compressed any further. The infalling material rebounds off the core and explodes outward in a supernova, one of the most violent events in the universe. For a brief few weeks, Cephei will shine brighter than every other star in its galaxy combined. The explosion will be visible from Earth in broad daylight, assuming anyone is around to see it, and assuming it hasn't happened already. Light from Cephei takes at least 2,500 years to reach us. If the star exploded tomorrow, we wouldn't know for another 2,500 years. If it exploded 2,499 years ago, we'll find out next year. The supernova could already be on its way, a wave front of light racing toward Earth at 186,000 miles per second, carrying the final image of a star that died millennia ago, while ancient civilizations were just learning to smelt bronze. What's left after the explosion depends on the mass of the core. If the core is below about 3 solar masses, it will settle into a neutron star, a ball of neutrons roughly 30 kilometers across, spinning at hundreds of rotations per second and radiating beams of radiation from its magnetic poles. If the core is above 3 solar masses, even neutron degeneracy pressure won't be enough to stop the collapse. The core will keep contracting, past the point where atoms can exist, past the point where quantum mechanics can help, all the way down to a singularity, a black hole. Either way, the star is gone, the garnet glow is gone, the massive bloated envelope drifting lazily through space is gone. All that remains is a remnant, a cosmic tombstone marking the place where one of the largest stars in the galaxy used to be. Astronomers used to classify Cephei as the prototype of a class called Cephei variables, semi-regular pulsating stars with periods longer than a year. The classification is obsolete now, folded into the broader category of SRC variables, but the name reflects how unique the star seemed when it was first studied in detail. In 1943, the spectral type M2IAE was defined using Cephei as the standard reference, meaning every other star classified as M2IAE is being compared to this one. It's the benchmark, the definition of what a cool, luminous, massive, evolved star looks like. No planets have been detected around Mu Cephei. That's not surprising. Any planets that formed in the star's early days would have been incinerated or ejected when the star expanded into a red supergiant. The habitable zone, the region where liquid water could exist on a planet's surface, would have migrated outward by billions of miles as the star's luminosity increased. If there were planets in stable orbits far enough out to survive the expansion, they'd be frozen, irradiated worlds baking under the dim red glow of a dying star. There are other stars in the same class: NML Cygni, VY Canis Majoris, Wyoming Canis Majoris. All of them red supergiants or hypergiants, all of them among the largest stars known, all of them burning through their final reserves of fuel and shedding mass into space at rates that would empty the sun in a few million years. Mu Cephei is not unique. It's just one example of a type of object that shouldn't be able to exist for long and doesn't. These stars represent a brief, unstable phase of stellar evolution, a moment when gravity and radiation pressure are locked in a stalemate that can't last, a moment when a star swells to a size so absurd that light takes most of an hour to cross it. And you can see it, right now, tonight, if the sky is clear and you know where to look. It's there, glowing faintly red in Cepheus, 1,500 times wider than the sun, radiating 250,000 times more energy, slowly tearing itself apart in preparation for the explosion that will end it. Herschel saw it in the 1780s with a homemade telescope. You can see it with your eyes, but it's not the only one, and it's not the most famous. There's another red supergiant, older, brighter, closer, and far more embedded in human mythology. A star that has been known since ancient times, not as a curiosity, but as a rival. A star that sits in the heart of the Scorpion, glowing like a warning. A star the Greeks called Antares, the equal of Mars, the anti-Aries. A star we've been watching for thousands of years, wondering what it is and what it will become. Antares. The ancient rival's glowing majesty. Antares, the ancient rival's glowing majesty. The Greeks looked up at the night sky and saw a red star glowing in the heart of Scorpius, the Scorpion. And they looked over at Mars, the red planet wandering slowly through the zodiac, and they noticed something. The star and the planet were nearly the same color, same intensity, same ominous glow. From the ground, without a telescope, without any way to measure distance or size or temperature, the two objects looked like equals. The Greeks, never ones to let a good rivalry go to waste, gave the star a name that translates roughly to the rival of Mars. In Greek, that's Antares, anti-Ares, the thing that stands against Ares, the god of war, the thing that dares to match him. This was not a casual observation. In ancient astronomy, Mars was significant. It moved against the background stars in strange looping patterns, brightening and dimming on an unpredictable schedule, glowing red like blood or rust. It was associated with conflict, violence, and disruption. To see a star that looked almost identical to Mars, sitting in one of the most prominent constellations visible from the Mediterranean, was to see a cosmic standoff. Two red lights, one wandering, one fixed, locked in an eternal staring contest. The name stuck. More than 2,000 years later, we still call it Antares, even though we now know the comparison is absurd. Mars is a planet, a small, cold, rocky world with a diameter of about 4,200 miles, no atmosphere worth mentioning, and a surface covered in iron oxide dust that gives it the red color ancient observers noticed. Antares is a star, a red supergiant more than 680 times wider than the Sun, radiating somewhere between 75,000 and 100,000 times more energy, hot enough to vaporize any known substance, and sitting roughly 550 light-years from Earth. The two objects have nothing in common except the color, and even that is misleading, because the red you see when you look at Mars is reflected sunlight bouncing off rust. The red you see when you look at Antares is thermal radiation from a star so enormous that if you placed it where the Sun is right now, its surface would extend past the orbit of Mars and possibly reach Jupiter. Let that sink in for a second. The planet Mars, the thing the Greeks thought this star rivaled, would be inside the star. Mars orbits the Sun at an average distance of about 142 million miles. Antares has a radius estimated at somewhere between 680 and 700 times the radius of the Sun. The Sun's radius is about 432,000 miles. Multiply that by 680 and you get roughly 294 million miles. That's the radius, not the diameter. The full width of the star, from one side to the other, would be around 588 million miles. Mars would not be a rival. Mars would be a speck of ash drifting through the outer layers of Antares, vaporized within seconds of crossing into the star's extended atmosphere. Antares sits in the constellation Scorpius, which is one of the few constellations that actually looks like the thing it's named after. If you're watching from the southern hemisphere or the southern United States during summer, Scorpius is hard to miss. It curves across the sky in a long arc, tail and stinger included, with Antares marking the heart of the Scorpion. The star is bright, ranking as the 15th brightest object in the night sky, not counting the Sun or the Moon. Its apparent magnitude varies between about 0, 6 and 1. 6 depending on where it is in its pulsation cycle, but even at its dimmest it's still prominent. You don't need a telescope. You don't need a star chart. If you know where Scorpius is, you can find Antares just by looking for the brightest red star in that part of the sky. What you're seeing when you look at Antares is light that left the star sometime around the year 1474, give or take a few decades depending on the exact distance. That's roughly the time Christopher Columbus was planning his first voyage to the Americas. The light took 550 years to cross the void between that star and your eyeball. It's old light, and it's telling you a story about a star that may no longer exist in the form you're seeing it. Antares could have exploded as a supernova at some point in the last 5 centuries, and we wouldn't know yet. The explosion, if it happened, is still in transit, racing toward Earth at the speed of light, but not here yet. For all we know, the star is already gone, and we're looking at a ghost. But let's assume it's still there. Let's assume the star we're seeing tonight is the star as it exists right now, modulo the 550-year light travel delay. What exactly are we looking at? Antares is classified as a red supergiant with a spectral type of M1, 5 Iab Ab. The M means it's cool, at least by stellar standards. The surface temperature sits around 3,660 Kelvin. For comparison, the Sun's surface is about 5,772 Kelvin. The difference doesn't sound dramatic until you realize that in stellar physics, a couple thousand degrees completely changes the star's appearance. A hotter star emits most of its light in the visible spectrum. A cooler star shifts most of its output into the infrared. Antares is cool enough that a huge fraction of its energy is invisible to human eyes. What we see as a dim red glow is only a tiny slice of the total radiation pouring off the star's surface. If you could see in infrared, Antares would be blindingly bright, one of the most luminous objects in the night sky. The mass of Antares is estimated at around 12 solar masses, though some studies push it as high as 14, 3. That might sound modest compared to the most massive stars known, which can weigh 100 or even 200 solar masses, but remember, this star didn't start at 12 solar masses, it started much heavier. Current estimates suggest the progenitor star, the main sequence object that eventually became Antares, weighed somewhere between 15 and 17 solar masses. It's lost several solar masses worth of material over the course of its life, blown away by stellar winds and radiation pressure as the star evolved off the main sequence and expanded into a red supergiant. That mass loss is ongoing. Antares is shedding material right now, continuously, at a rate that would horrify any star trying to maintain structural stability. The stellar wind carries away gas from the outer layers of the star, enriching the surrounding space with heavy elements forged in the star's core. Over millions of years, that material will drift outward, mix with the interstellar medium, and eventually get incorporated into the next generation of stars and planets. The carbon in your body, the oxygen you're breathing, the iron in your blood, all of it was made inside stars like Antares and scattered into space when those stars died. You are, quite literally, made of dead stars. Antares is in the process of contributing its share to the cosmic recycling program. The luminosity of Antares is where things get truly absurd. Depending on which study you trust and how you account for the infrared radiation, the total energy output ranges from about 75,900 to 100,000 times the luminosity of the Sun. Some estimates push it as high as 128,900 solar luminosities. Let's stick with the conservative figure of 75,900. That means Antares is radiating as much energy in 1 second as the Sun produces in roughly 21 hours, every second. The star is not burning hydrogen in its core anymore. It exhausted that fuel millions of years ago. It's burning helium, or possibly heavier elements like carbon and oxygen, depending on how far along it is in its evolutionary track. Each stage of fusion releases less energy than the one before, but the star compensates by ramping up the rate of fusion and expanding its outer layers to shed the excess heat. The result is a star that's extraordinarily bright but structurally unstable. The outer atmosphere is so diffuse that it barely qualifies as a surface in the way we normally think of surfaces. The density is closer to what you'd find in a laboratory vacuum chamber than in any solid or liquid material. If you could somehow fly a spaceship through the outer layers of Antares, you wouldn't notice when you crossed the boundary. The gas around you would gradually get thicker and hotter as you descended, but there would be no sharp edge, no moment where you'd say, okay, now we're inside the star. You'd just keep falling deeper into an increasingly hot, increasingly dense fog of hydrogen and helium until the temperature got high enough to vaporize your spacecraft and everyone inside it. Astronomers have been trying to measure the size of Antares accurately for more than a century, and the results have been all over the place. The first serious attempt came in 1925 when Francis G. Pease used an interferometer at the Mount Wilson Observatory to measure the star's angular diameter. He got a value of about 463 to 497 solar radii, which at the time made Antares the largest star known. The measurement was groundbreaking because it was the first time anyone had directly resolved the disk of a star other than the Sun. Up until that point, even the largest stars appeared as single points of light through the best telescopes available. Interferometry changed that by combining the light from multiple mirrors or telescopes to simulate a much larger instrument, allowing astronomers to measure the apparent size of nearby giant stars with enough precision to calculate their true diameters. Since then, the estimates have climbed. Modern studies using more sophisticated techniques put the radius somewhere between 680 and 700 solar radii. though the exact number depends on how you define the edge of the star. The outer atmosphere of a red supergiant is not a clean boundary. It's a gradual transition from the hot, dense inner layers to the cool, diffuse outer envelope, and there's no universal agreement on where you draw the line. Some measurements focus on the photosphere, the layer where most of the visible light escapes. Others include the extended atmosphere, which can stretch much farther out. A 2013 imaging study found that the outer atmosphere extended to about 2 to 1, 4 times the photospheric radius, adding tens of millions of miles to the effective size of the star. What makes Antares particularly interesting and particularly frustrating to measure is that it's a variable star, not a regular pulsating variable like a Cephei, but a slow, irregular variable. The brightness changes over time, dipping and brightening on no fixed schedule. The surface temperature fluctuates, the radius expands and contracts. The whole structure is in a state of barely controlled chaos, driven by instabilities deep inside the star where fusion is happening in shells around an inert core. That variability makes it difficult to pin down a single number for the star's size or luminosity. You're not measuring a static object. You're measuring a dynamic, evolving system that's different every time you look at it. Antares is also a binary system, though the companion star is so much fainter that it's almost irrelevant to the overall picture. The companion Antares B is a B-type main sequence star with a spectral type around B25V. It's hotter than the Sun, bluer and more massive, but it's completely outshone by the red supergiant primary. The two stars orbit each other at a separation of about 529 astronomical units, which translates to roughly 49 billion miles. That's more than 10 times the distance from the Sun to Pluto. At that distance, the gravitational influence between the two stars is weak, and the companion doesn't seem to have much effect on the evolution of the red supergiant. It's just along for the ride, orbiting quietly in the shadow of its vastly more luminous partner. The companion was discovered in 1847 by Johann Georg Friedrich von Madler, a German astronomer who was systematically cataloguing double stars. Detecting it was a technical challenge because Antares A is so much brighter that the glare makes it nearly impossible to see anything nearby. You need excellent atmospheric conditions, a telescope with enough resolving power to separate the two stars, and a bit of luck. Even today, with modern instruments, observing Antares B requires careful planning and image processing to subtract the overwhelming light from the primary star. What the ancient Greeks saw when they looked at Antares was a single red point of light, indistinguishable from Mars to the naked eye. What we see when we point a modern telescope at it is a complex system, a bloated red supergiant losing mass through a powerful stellar wind, surrounded by a diffuse envelope of gas and dust, orbited by a smaller but still respectable main sequence star, all of it sitting at a distance of 550 light-years, glowing with the combined output of 75,000 suns. The Greeks had no idea, they couldn't have. But they noticed the color, and they noticed that it matched Mars, and they gave it a name that honored the resemblance. In their ignorance, they stumbled onto something true. Both objects are red. Both objects stand out. And in the grand scale of the universe, both objects are utterly insignificant specks. Mars is a dead rock. Antares is a dying star. Neither one is a rival to anything except our own inflated sense of importance. But here's the thing, for all its size, for all its luminosity, Antares is not even close to the largest star we've found. It's big, it's bright, it's been known to humanity for thousands of years, which gives it a kind of historical weight that newer discoveries don't have. But in the race for cosmic supremacy, Antares doesn't even make the top 5. The radius of 680 to 700 solar radii is impressive, but there are stars out there with radii exceeding 1,000 solar radii, stars that would make Antares look small by comparison. Stars that we didn't even know existed until the last few decades because they're so far away and so heavily obscured by dust that they barely registered in visible light surveys. One of those stars sat in the constellation Canis Major for centuries, glowing faintly red, ignored by almost everyone who looked at it. No ancient mythology, no dramatic name. Just a designation in a catalogue, notable only to a handful of professional astronomers who bothered to measure it. And when they did measure it, when they finally figured out how far away it was and how much light it was actually producing, the numbers came back wrong. Too big, too bright, too far outside the expected range for a normal star. For a brief period in the late 20th and early 21st centuries, this star held the title of the largest known object in the universe. Not the most massive, not the brightest, the largest, the biggest physical object humanity had ever confirmed. A star so enormous that if you tried to comprehend its scale, your brain would give up halfway through the calculation and suggest you go do something easier, like count grains of sand on a beach. That star is VY Canis Majoris, and it used to be the king. VY Canis Majoris, the former king's reign for a brief period, from the late 1990s until sometime in the mid-2010s, VY Canis Majoris held the title of the largest known star in the universe. Not the brightest, not the most massive, the largest, the biggest physical object humanity had ever measured. A star so enormous that the numbers describing it stopped feeling like measurements and started feeling like typos. And then better instruments came along. Better measurements, better understanding of how to interpret the fuzzy, obscured, infrared-soaked data coming from objects like this. And the title slipped away. VY Canis Majoris was demoted, downgraded, knocked off the throne it had occupied for more than a decade. The king became the former king, and the story of how that happened is as interesting as the star itself. VY Canis Majoris sits in the constellation Canis Major, the larger of the two hunting dogs following Orion across the winter sky. Canis Major is famous mostly because it contains Sirius, the brightest star visible from Earth. VY Canis Majoris is not famous, it's not bright. You can't see it with your naked eye, unless you have exceptional vision, a perfectly dark sky, and the patience to stare at the right patch of nothing until your eyes adjust. At its brightest, the star reaches a visual magnitude of about 6.5, right at the edge of naked eye visibility. Most of the time it's dimmer than that, fading to magnitude 9.6 during its irregular pulsation cycle. You need binoculars at minimum, and preferably a telescope, to pick it out from the background stars. The star sits roughly 3,900 light-years from Earth. That distance estimate has bounced around over the years as parallax measurements improved, but the current best guess lands somewhere between 3,900 and 3,930 light-years, depending on which study you trust. It's far enough that the light reaching your telescope tonight left the star around the time humans were just starting to figure out how to smelt bronze. Far enough that any supernova explosion, if it's already happened, is still in transit and won't arrive for centuries or millennia. The first person to catalogue VY Canis Majoris was a French astronomer named Jérôme Lalande, who noted it on March 7, 1801, as a 7th magnitude object. Lalande was in the middle of compiling a massive star catalogue, one of the most ambitious projects of the era, and VY Canis Majoris was just another entry on a very long list. He marked it down, moved on, and that was that. The star sat quietly in the catalogue for the next 150 years, ignored by almost everyone, just another faint red dot in a part of the sky full of faint red dots. By the mid-19th century, a few astronomers noticed the star was doing something odd. It was surrounded by faint nebular patches, little glowing clouds that seemed to be attached to or near the star itself. Some observers working with the relatively primitive telescopes of the time suspected VY Canis Majoris might actually be multiple stars clustered together, each one contributing to the glow. That hypothesis lasted until 1957, when better observations confirmed it was a single star. The nebular patches weren't separate objects. They were part of the star's extended atmosphere or debris field, material that had been shed by the star itself over thousands of years and was now drifting outward into space, glowing faintly from the radiation still leaking out of the core. The real breakthrough came in 1998, when astronomers finally imaged the star directly with enough resolution to confirm, beyond any doubt, that this was one object, not several. And once they had that confirmation, they could start taking the measurements seriously, and the measurements were absurd. The radius of VY Canis Majoris, depending on which study you cite and how you account for the extended atmosphere and the mass loss envelope and the infrared excess and all the other complications that make these measurements a nightmare, falls somewhere between 1,420 and 2,000 solar radii. The most commonly cited figure is around 1,420. Let's use that. If you replaced the Sun with VY Canis Majoris, the star's surface would extend past the orbit of Jupiter. Some of the more aggressive estimates push the surface out near Saturn. You would not be living in a solar system anymore. You would be living inside a star. The diameter from one side of the star to the other comes out to roughly 2 billion kilometers. Light, traveling at 300,000 kilometers per second, would take about 6 hours to cross from one edge to the other. Not 6 minutes, not 6 seconds, 6 hours. For the fastest thing in the universe to cross a single object. Wrap your head around that for a second. A photon leaves the surface of VY Canis Majoris, travels in a straight line at the maximum speed allowed by physics, and 6 hours later, it finally clears the far side of the star and continues into open space. That's not a star, that's a region. The volume is even worse. If you could somehow hollow out VY Canis Majoris, you could fit roughly 3 billion suns inside the empty shell before you ran out of room. Not 3 million, 3 billion. You could take Betelgeuse, one of the most famous red supergiants in the sky, and fit about 8 copies of it inside VY Canis Majoris with space left over. You could take Antares, the star the Greeks thought rivaled Mars, and drop it into VY Canis Majoris, and it would rattle around like a marble in a gymnasium. And here's the thing that makes VY Canis Majoris particularly maddening for anyone trying to understand it. The star is not stable. The radius is not a fixed number. The surface, if you can even call it a surface, is constantly fluctuating, pulsating, expanding and contracting over a period of about 956 days. That's roughly 2.5 years per cycle. The brightness changes too, swinging between magnitude 6, 5 and 9. 6 with no predictable pattern. Astronomers have classified it as a slow, irregular variable, meaning the pulsations don't follow a clean periodic rhythm like a Cephei or a mirror-type star. The star just kind of wobbles, brightens, dims, wobbles some more, on a schedule only it understands. The classification itself is disputed. The General Catalogue of Variable Stars lists VY Canis Majoris as a semi-regular variable, type SRC. The American Association of Variable Star Observers classifies it as a slow, irregular variable, type LC. These are not trivial distinctions. They reflect genuine disagreement about what kind of physical process is driving the variability. Is the star pulsating in a semi-regular way that we just haven't figured out yet? Or is the whole structure so chaotic and so unstable that calling it regular in any sense is a mistake? Nobody knows for sure. The data is messy. The star is obscured by its own mass loss envelope. Every measurement comes with error bars wide enough to drive a truck through. The mass of VY Canis Majoris is estimated at around 17 solar masses, though some studies push it higher. That might sound modest compared to the star's physical size, but remember, this star started out much heavier. It's been losing mass for a long time, shedding material through powerful stellar winds that strip away the outer layers and blow them into space. The current estimate is that the star is losing mass at a rate of about 30 times the mass of Earth every single year. That's not a metaphor. Every year, the equivalent of 30 Earths worth of gas gets ripped off the surface of VY Canis Majoris and flung outward at speeds of several kilometers per second, pushed by radiation pressure from the core. That mass loss is one of the reasons measuring the star's size is so difficult. When you point a telescope at VY Canis Majoris, you're not just looking at the star. You're looking at the star plus a thick, dusty, asymmetric envelope of gas and debris surrounding it, glowing faintly from the star's radiation and blocking a huge fraction of the visible light. The envelope extends outward for thousands of astronomical units, blurring the boundary between where the star ends and where space begins. Trying to measure the radius of the star itself is like trying to measure the size of a light bulb hidden inside a thick cloud of smoke. You can estimate, you can model, but you can't see the light bulb directly. The surface temperature of VY Canis Majoris is somewhere between 3,200 and 3,490 Kelvin, depending on which part of the star you're measuring and when you measure it. For comparison, the Sun's surface sits at about 5,500 Kelvin. VY Canis Majoris is cooler, which is why it glows red instead of yellow or white. That cool temperature is also why the star radiates most of its energy in the infrared rather than the visible spectrum. If you looked at VY Canis Majoris with human eyes from a safe distance, you'd see a dim red glow, unimpressive and easy to miss. If you looked at it with an infrared camera, it would be one of the brightest objects in that entire region of the sky. VY Canis Majoris is the brightest local object in the 5 to 20 micron wavelength range, outshining everything around it by a ridiculous margin. The total luminosity, accounting for all wavelengths, is somewhere between 178,000 and 400,000 times the luminosity of the Sun. The range is wide because calculating luminosity requires knowing the distance, the temperature, the radius, and the amount of light being absorbed and re-radiated by the surrounding dust. And every one of those numbers has uncertainty built into it. But even the low end of the estimate is staggering. 178,000 times the Sun's output means VY Canis Majoris is radiating as much energy in 1 second as the Sun produces in about 2 days. The high end of the estimate is more than twice that. The star is pumping out energy at a rate that makes the Sun look like a desk lamp. This is a hypergiant, not a supergiant, a hypergiant. The classification is reserved for the most massive, most luminous, most unstable stars in the galaxy, stars that sit at the absolute edge of what stellar physics allows, stars that are losing mass so fast they might not survive long enough to finish their normal evolutionary track. VY Canis Majoris is classified as M5, which places it among the coolest hypergiants known. Most hypergiants are hotter, bluer, and more compact. VY Canis Majoris is a red hypergiant, which is a rarer and more extreme version of an already extreme class of object. The star started its life as a hot, bright, blue O-class star with a mass roughly twice what it has now. It spent a few million years on the main sequence, fusing hydrogen into helium in its core, burning through its fuel at a catastrophic rate. Then the hydrogen ran out. The core contracted. The outer layers expanded. The star left the main sequence and began fusing helium. Then helium ran out. The core contracted again. The star expanded further, growing larger and cooler as it climbed the evolutionary ladder, fusing heavier and heavier elements in a desperate attempt to generate enough pressure to hold itself up against gravity. Right now, Canis Majoris is probably fusing carbon or oxygen in its core, possibly neon or magnesium, depending on how far along it is in the process. Each stage releases less energy than the one before. Each stage happens faster. The star is running out of time. At some point, probably within the next few 100,000 years, it will reach the end of the line. The core will fill with iron, fusion will stop, gravity will win, and the star will explode. Except it might not explode in the way most supernovae do. Canis Majoris is so massive and so bloated that some models predict it will produce a hypernova, a supernova on steroids, releasing 10 to 100 times more energy than a typical core collapse event. Other models suggest the core might be so massive that even a supernova won't be enough to stop the collapse. The core will blow through neutron degeneracy pressure and keep falling all the way down to a singularity, forming a black hole without ever producing the characteristic outward explosion. If that happens, the star will just vanish. One day it's there, a massive red hypergiant dominating its corner of the sky. The next day, nothing. Just a black hole where a star used to be, surrounded by a faint, glowing shell of debris. The star is embedded in a massive molecular cloud called She-2310, which spans about 480 arc-minutes of the sky. It's also located near a young open cluster called NGC 2362, though it's not clear if Canis Majoris is actually a member of the cluster or just happens to be in the same line of sight. The star is young, less than 10 million years old, which is almost nothing in cosmic terms. The Sun is 6 billion years old. Canis Majoris has existed for less than 1/5 of 1% of that time, and it's already nearly dead. That's the price of being massive. You burn bright, you burn fast, and you don't last. No exoplanets have been detected around Canis Majoris. That's not surprising. Any planets that formed in the star's early days would have been vaporized or ejected when the star expanded into a hypergiant. The habitable zone, the narrow band where liquid water could exist on a planet's surface, has migrated outward by billions of kilometers as the star's luminosity increased. If there were planets in stable orbits far enough out to survive, they'd be frozen, irradiated wastelands bathed in the dim red glow of a dying star. One of the most interesting features of Canis Majoris is its spectral lines. The hydrogen lines show what astronomers call P Cygni profiles, a specific pattern of absorption and emission that's typically associated with luminous blue variables, not red hypergiants. A P Cygni profile indicates that material is being ejected from the star at high speed, creating a shell of gas that absorbs some wavelengths of light while emitting others. The presence of this feature in a red hypergiant is unusual and suggests that the mass loss process is even more violent and complex than standard models predict. Canis Majoris was also one of the first stars where astronomers detected radio masers, regions of the surrounding gas where molecules are amplifying specific wavelengths of radio emission, the way a laser amplifies light. The masers in Canis Majoris are produced by water vapor, silicon monoxide, and other molecules in the extended atmosphere. Studying these masses has allowed astronomers to map the structure of the mass loss envelope in extraordinary detail, revealing a chaotic asymmetric distribution of gas and dust that doesn't match the clean spherical shells predicted by early models. The debate over VY Canis Majoris's exact size has been going on for more than 2 decades, and it's still not settled. Early estimates in the late 1990s pushed the radius as high as 2,000 or even 2,500 solar radii, making the star by far the largest known object in the universe. Those estimates were based on models that assumed a relatively simple spherical geometry for the star and its surrounding envelope. As better data came in, the models got more sophisticated and the estimates came down. By the mid-2010s, the consensus had shifted to around 1,420 solar radii, which is still enormous but no longer the undisputed champion. Part of the problem is defining what you mean by the star's radius. Do you measure to the photosphere, the layer where most of the visible light escapes? Do you include the extended molecular atmosphere? Do you count the mass loss envelope? Different studies use different definitions, and the answers can vary by hundreds of solar radii depending on which boundary you choose. There's no universal standard, which means every new study has to specify exactly what it's measuring before the number means anything. And then better instruments found other stars farther away, more heavily obscured, harder to measure. Stars that, once the dust cleared and the models settled, turned out to be even larger than VY Canis Majoris. Stars like Scuti, a red supergiant in the constellation Scutum that briefly held the title of largest known star after VY Canis Majoris was downgraded. Stars like Stephenson 218, a hypergiant buried so deep inside a massive star cluster that astronomers didn't even know it existed until the late 20th century. VY Canis Majoris was the king. It sat at the top of the list for more than a decade, unchallenged, the biggest thing anyone had ever found. And then the crown slipped. Not because the star got smaller, but because we got better at measuring, and we found things that were bigger. But here's the thing, losing the title doesn't make VY Canis Majoris any less remarkable. It's still one of the largest stars in the galaxy. It's still radiating hundreds of thousands of times more energy than the Sun. It's still shedding 30 Earths worth of mass every year. It's still dying in one of the most violent and spectacular ways a star can die. It's still out there, glowing faintly red in Canis Major, ticking down the clock toward an explosion that will, for a few brief weeks, make it one of the brightest objects in the galaxy. The demotion is a reminder that astronomy is not a static field. The biggest, the brightest, the farthest, all of those titles are temporary. Every new telescope, every new technique, every refinement in how we measure distance or size or luminosity shifts the rankings. What we think we know today is the best guess we can make with the tools we have. Tomorrow the tools get better, and the guess changes. VY Canis Majoris was the king. Now it's the former king. And somewhere out there, probably buried inside a dense molecular cloud or hidden behind a thick veil of dust, there's a star even larger than VY Canis Majoris that we haven't found yet. Or maybe we have found it. Maybe it's sitting in a catalogue right now, listed as a faint infrared source, waiting for someone to take a closer look and realize what they're seeing. That's how these things go. The universe is full of monsters. We just have to know where to look. Scuti, the dethroned monarch's story, VY Canis Majoris was the king. Then it wasn't. The measurements tightened, the instruments improved, and the throne changed hands. The new king, for a while at least, was a star most people had never heard of. A dim red supergiant sitting in a constellation so obscure that even amateur astronomers sometimes forget it exists. Its name was Scuti, and for a brief shining moment in the mid-2010s, it held the title of the largest known star in the universe. Media outlets picked up the story. YouTube channels made videos with thumbnails showing a bloated red sphere swallowing entire planetary systems. Articles declared it the biggest thing humanity had ever measured, a star so enormous that if you placed it where the Sun is right now, its surface would stretch past the orbit of Jupiter and possibly reach Saturn. The numbers were extraordinary, the images were dramatic, and the science, as it turned out, was messier than anyone wanted to admit. Scuti was not a new discovery. Astronomers at the Bonn Observatory in Germany catalogued it back in 1860 as part of a routine survey of the southern sky. It was listed as a faint variable star in the constellation Scutum, a small, shield-shaped pattern squeezed between Aquila and Sagittarius. Scutum is not a famous constellation. It doesn't have any bright stars. It doesn't have any mythology attached to it. It was invented in the 17th century by a Polish astronomer who wanted to honor a king, and it has been sitting quietly in the southern sky ever since, ignored by almost everyone except professional star mappers and the kind of amateur astronomers who pride themselves on knowing every single constellation, even the boring ones. Scuti sat in that constellation for more than 150 years, glowing faintly red, pulsating on an irregular schedule, occasionally brightening enough to be picked up by variable star observers, and otherwise minding its own business. Nobody thought it was special. Nobody thought it was worth more than a footnote in a catalogue. Then in 2012, a team of astronomers used the Very Large Telescope in Chile, one of the most powerful ground-based observatories in the world, to measure the angular diameter of Scuti using a technique called interferometry. Interferometry works by combining the light from multiple telescopes to simulate a single gigantic telescope with a much larger effective diameter. The technique allows astronomers to resolve objects that would otherwise appear as single points of light, measuring the apparent size of the star's disk on the sky with extraordinary precision. The VLT team pointed their instrument at Scuti, measured the angular diameter, calculated the distance using the best available data, and ran the numbers. The result they got was somewhere around 1,700 solar radii. If that number held up, it would make Scuti significantly larger than Canis Majoris, not by a small margin, by hundreds of solar radii, enough to move it from contender to champion. The radius estimate of 1,700 times the Sun's radius translates to about 188 billion kilometers. That's the radius, not the diameter. The full width of the star, from one side to the other, comes out to roughly 376 billion kilometers. For context, the distance from the Sun to Jupiter is about 778 million kilometers. The distance from the Sun to Saturn is about 4 billion kilometers. If you placed Scuti where the Sun is right now, the star's surface would engulf Mercury, Venus, Earth, Mars, the asteroid belt, and Jupiter. Depending on which part of the pulsation cycle the star was in, the surface might extend far enough to swallow Saturn too. That's not a solar system anymore. That's a single object occupying the space where an entire planetary system used to be. The volume is where the scale really breaks your brain. If you could hollow out Scuti and fill it with suns, you would need roughly 5 billion of them before you ran out of space. Not 5 million, 5 billion. That's more than the number of people currently living on Earth. That's roughly the number of years the Sun has left before it exhausts its hydrogen fuel and begins expanding into a red giant. That's a number so large that trying to visualize it is pointless. You just have to accept it as a fact and move on. The mass of Scuti, by contrast, is not particularly impressive. Current estimates put it somewhere between 7 and 10 solar masses, depending on which model you trust and how much mass the star has already shed through stellar winds. That might sound contradictory. How can a star weigh only 7 to 10 times as much as the Sun, but be 1,700 times larger? The answer is density, or rather the lack of it. The outer layers of a red supergiant are so diffuse that they barely qualify as matter in the way we normally think of matter. The density in the outer atmosphere of Scuti is lower than the best laboratory vacuum we can create on Earth. If you could somehow fly a spaceship through the outer layers of the star, you wouldn't notice when you crossed the boundary. The gas around you would just gradually get thicker and hotter as you descended deeper into the star's envelope, and by the time you realized you were inside, you'd already be dead. The surface temperature of Scuti sits somewhere between 3,365 and 3,550 Kelvin, depending on which part of the pulsation cycle the star is in and how you define the surface. That's cool by stellar standards, which is why the star glows red instead of yellow or white. The Sun's surface temperature is about 5,778 Kelvin, nearly twice as hot. A cooler surface means the star emits most of its energy in the infrared rather than the visible spectrum. If you looked at Scuti with human eyes from a safe distance, you'd see a dim red glow, unimpressive and easy to miss. If you looked at it with an infrared camera, it would be one of the brightest objects in that region of the sky, radiating heat at a rate that makes the Sun look like a candle. The total luminosity of Scuti, accounting for all wavelengths, ranges from about 124,000 to 340,000 times the luminosity of the Sun. The range is wide because calculating luminosity requires knowing the distance, the temperature, the radius, and the amount of light being absorbed and re-radiated by the surrounding dust. Every one of those numbers has uncertainty built into it, and the uncertainties compound, but even the low end of the estimate is staggering. 124,000 times the Sun's output means Scuti is radiating as much energy in 1 second as the Sun produces in roughly 34 hours. The high end of the estimate is nearly 3 times that. The absolute magnitude, a measure of how bright the star would appear if you placed it exactly 10 parsecs away, sits around -6.2. For comparison, the Sun's absolute magnitude is 4.83. That's a difference of more than 11 magnitudes, which translates to a brightness ratio of roughly 100,000 to 1. Scuti is a pulsating variable star, classified as a semi-regular variable with a period of about 740 days. That's just over 2 years per cycle. The brightness fluctuates between magnitude 8, 29 and 10, 56, a range of more than 2 magnitudes. At its brightest, the star is too faint to see with the naked eye unless you have exceptional vision and a perfectly dark sky. At its dimmest, you need a decent amateur telescope to pick it out from the background stars. The pulsations are driven by instabilities in the star's structure, where the outer layers expand and contract as the core struggles to maintain equilibrium between the inward pull of gravity and the outward push of radiation pressure. The whole process is chaotic, irregular, and barely under control. The star is not stable, it's dying, and it's doing it loudly. The classification of Scuti as a supergiant or a hypergiant is still debated. Some sources list it as a red supergiant, others as a red hypergiant. The distinction matters because hypergiants are a separate, more extreme class of object, reserved for the most massive, most luminous, most unstable stars in the galaxy. Scuti's luminosity and size put it right on the boundary between the two categories. It's bright enough and large enough to qualify as a hypergiant, but its mass is relatively low, which complicates the classification. Astronomers have not reached a consensus, and different catalogues list it differently depending on which criteria they prioritize. The distance to Scuti is one of the biggest sources of uncertainty in all the measurements. Early estimates placed the star somewhere between 5,000 and 9,500 light-years from Earth. That's a huge range, and distance matters because every other calculation depends on it. If the star is closer, it must be smaller and dimmer to appear as faint as it does from Earth. If it's farther away, it must be larger and brighter. The 2012 VLT study that crowned Scuti as the largest known star used a distance estimate of about 9,500 light-years. That distance, combined with the measured angular diameter, gave a radius of roughly 1,700 solar radii. But the distance was not a direct measurement. It was an estimate based on the star's spectral type, its brightness, and assumptions about how much light was being absorbed by interstellar dust along the line of sight. All of those assumptions carried uncertainty. Then the Gaia spacecraft came along. Gaia is a European Space Agency mission designed to map the positions and distances of more than 1 billion stars with unprecedented precision. It uses a technique called parallax, measuring the tiny apparent shift in a star's position as Earth orbits the Sun. The closer the star, the larger the shift. Gaia can measure parallaxes accurate to within a few microarcseconds, which translates to distance measurements good to within a few % for stars within a few thousand light-years. For stars farther away, the parallax becomes too small to measure accurately, and the uncertainties grow. Scuti sits near the edge of Gaia's range, and the parallax measurement came back with large error bars. But the central value suggested the star might be closer than 9,500 light-years. Some analyses of the Gaia data put the distance closer to 5,000 or 6,000 light-years. If Scuti is closer, the radius estimate drops. Using a distance of around 5,900 light-years, which is near the middle of the revised range, the radius comes out to somewhere around 900 to 1,000 solar radii instead of 1,700. That's still enormous. That's still one of the largest stars known. But it's not the largest, and that's how the dethronement happened. Not because Scuti physically changed, but because the measurements got better and the distance estimate shifted. The star didn't shrink, the uncertainty narrowed, and the title slipped away. The problem with measuring stars like Scuti is that everything about them is difficult. They're far away, so the parallax is tiny and the measurement is noisy. They're heavily obscured by dust, both in the surrounding interstellar medium and in the thick shells of gas and debris they've ejected themselves, so the light reaching Earth is dimmed and reddened in ways that are hard to correct for. They're variable, so the brightness, the radius, and even the temperature change over time, making it impossible to pin down a single number that represents the star. And they're embedded in regions of active star formation, surrounded by molecular clouds and bright nebulae, which makes it hard to isolate the star's light from everything else in the field of view. Every measurement comes with caveats, every estimate comes with error bars, and every new study that refines one piece of the puzzle tends to shift the others. The Very Large Telescope study that first measured Scuti's angular diameter was groundbreaking because it was the first time anyone had directly resolved the star's disk. Prior to that, all size estimates were indirect, based on models that assumed certain properties about the star's temperature, luminosity, and evolutionary state. The interferometry measurement removed some of those assumptions, providing a direct observation of the star's apparent size on the sky. But the measurement itself was not perfect. Interferometry works best when the object being measured is simple and symmetric. like a clean circular disk. Scuti is neither simple nor symmetric. It's a pulsating, irregular, mass-losing hypergiant surrounded by a dusty, asymmetric envelope. The edge of the star is not a sharp boundary. It's a gradual transition from the hot, dense inner layers to the cool, diffuse outer atmosphere, and there's no universal agreement on where you draw the line. Different wavelengths probe different layers of the star, and the size you measure depends on which layer you're looking at. Measuring the star in the infrared gives you a larger radius than measuring it in visible light, because the infrared probes the cooler outer layers. Accounting for the extended atmosphere adds even more to the effective size. The 1,700 solar radii figure was based on a specific set of assumptions about where the photosphere is and how to interpret the interferometric data. Change the assumptions, and the number changes. The revised estimates based on the Gaia distance and more sophisticated models of the star's atmosphere tend to cluster around 900 to 1,000 solar radii. Some studies push it as low as 750 solar radii. Others keep it closer to 1,200. The range depends on which dataset you trust, which model you use, and how you account for the dust and the pulsations and all the other complications that make this measurement a nightmare. But the consensus has shifted. Scuti is no longer the largest known star. It's still one of the largest. It's still enormous by any reasonable standard, but it's not the champion anymore. The media took a while to catch up. For years after the revised measurements came out, articles and videos continued to cite Scuti as the largest star, often using the old 1,700 solar radii figure without mentioning the uncertainty or the updated estimates. The image of a star so large it would swallow Saturn was too good to let go. The truth that the star is probably only large enough to swallow Jupiter and maybe a bit beyond is still impressive but less dramatic, and drama sells. So the old number stuck around in popular science articles and YouTube videos long after the professional literature had moved on. This is not unusual in astronomy. Titles like largest, brightest, farthest, most massive, all of them are temporary. They reflect the best measurements available at the time with the instruments and techniques we currently have. Every new telescope, every new satellite, every refinement in how we measure distance or brightness or size shifts the rankings. What we think is the largest star today might be the second or third largest star tomorrow, once someone takes a better look at a different object or refines the distance estimate to a known giant. The universe does not hand out permanent titles. We do, and we revise them constantly as the data improves. Scuti is still out there, glowing faintly red in scutum, pulsating on its 740-day cycle, losing mass through powerful stellar winds, ticking down the clock toward a supernova that will happen sometime in the next few 100,000 years. The star is probably in the late stages of helium fusion, possibly moving into carbon fusion, depending on how far along it is in its evolutionary track. Once it exhausts its fuel, the core will collapse, and the outer layers will explode in a supernova that will, for a few brief weeks, make Scuti one of the brightest objects in the galaxy. And then it will be gone, leaving behind either a neutron star or a black hole, depending on how massive the core turns out to be. The dethronement of Scuti is a reminder that science is not a static process. The largest star is not a fixed object waiting to be discovered. It's a moving target, shifting every time the instruments get better or the measurements get more precise. Canis Majoris was the largest for a while. Then Scuti took the title. Then the measurements improved, and Scuti lost it. And somewhere out there, buried in the data from the latest surveys, there's probably another star even larger than Scuti, waiting for someone to take a closer look and realize what they're seeing. That star, as it turns out, has already been found. It's sitting in a massive star cluster roughly 20,000 light-years from Earth, hidden behind so much dust and gas that it barely registers in visible light. It's so heavily obscured that astronomers didn't even know it existed until the late 20th century, and it took another decade or more to measure it accurately enough to realize just how enormous it actually is. The cluster itself is extraordinary, containing some of the most massive and most luminous stars in the galaxy. And in the heart of that cluster, surrounded by a dense swarm of supergiants and hypergiants, sits the current reigning champion. A star so large that if you tried to fit it into the solar system, there wouldn't be a solar system left. A star that makes Scuti look modest. A star with a name that sounds more like a catalogue entry than a title. Stephenson 218. And it's the biggest thing we've ever measured. That star, as it turns out, has already been found. It's sitting in a massive star cluster, roughly 20,000 light-years from Earth, hidden behind so much dust and gas that it barely registers in visible light. It's so heavily obscured that astronomers didn't even know it existed until the late 20th century, and it took another decade or more to measure it accurately enough to realize just how enormous it actually is. The cluster itself is extraordinary, containing some of the most massive and most luminous stars in the galaxy. And in the heart of that cluster, surrounded by a dense swarm of supergiants and hypergiants, sits the current reigning champion. A star so large that if you tried to fit it into the solar system, there wouldn't be a solar system left. A star that makes Scuti look modest. A star with a name that sounds more like a catalogue entry than a title. Stephenson 218. And it's the biggest thing we've ever measured. The story of how we found Stephenson 218 is not a story of someone pointing a telescope at the sky and stumbling onto something extraordinary by accident. It's a story of systematic surveying, patient analysis, and the slow realization that something in the data didn't fit the expected pattern. The star sits inside an open cluster called Stephenson 2, named after Charles Bruce Stephenson, an astronomer at Case Western Reserve University, who first identified the cluster in the early 1990s while conducting a deep infrared survey of the Milky Way. Open clusters are groups of stars that form together from the same giant molecular cloud, bound loosely by gravity, slowly drifting apart over millions of years as the gravitational influence of the galaxy pulls them in different directions. Most open clusters contain a few hundred to a few thousand stars. Stephenson 2 is not most clusters. Stephenson 2 is the most massive open cluster in the Milky Way. The thing contains 26 red supergiants, the largest population of red supergiants ever found in a single cluster. That number is absurd. Red supergiants are rare. They represent a brief, unstable phase of stellar evolution that only the most massive stars pass through, and they only last a few 100,000 years before exploding as supernovae. Finding 26 of them in one place is like walking into a high school reunion and discovering that half your graduating class went on to become professional astronauts. It doesn't happen, except it did. The cluster sits in the constellation Scutum, the same obscure shield-shaped pattern where Scuti lives. Scutum is not a bright constellation, it's not a famous constellation. It sits low in the summer sky for Northern Hemisphere observers, squeezed between Aquila and Sagittarius, right in the densest part of the Milky Way where the galactic plane is thick with dust and gas and stars stacked on top of stars in layers so deep you can't see through them. This is not prime observing territory. The dust absorbs visible light, reddening and dimming everything behind it, turning bright stars into faint smudges and faint stars into nothing at all. If you want to study this region, you don't use an optical telescope, you use infrared. Infrared light passes through dust more easily than visible light, revealing objects that would otherwise be invisible. That's what Stephenson was doing. He was conducting an infrared survey, systematically mapping the sky, looking for clusters of bright infrared sources that might indicate regions of active star formation or groups of evolved massive stars. When he found the cluster that would later bear his name, he catalogued it, noted the unusual concentration of red supergiants, and published his findings. The cluster was assigned the designation Stephenson 2. The individual stars within it were numbered, and for a while that was that. The cluster was interesting, the stars were interesting, but nobody had measured them in enough detail to realize just how extreme some of them actually were. That changed in 2010 when a team led by Deguchi published a detailed analysis of the cluster using infrared photometry and spectroscopy. They measured the brightness, the temperature, and the distance to the stars in the cluster. They calculated luminosities. They estimated radii, and when they got to the 80th star on their list, the one now officially designated as Stephenson 218, the numbers came back wrong. Too bright, too large, too far outside the range where red supergiants are supposed to sit. The star was radiating about 440,000 times the luminosity of the Sun. That's more energy than the Humphreys-Davidson limit, the theoretical upper bound for how bright a red supergiant can get before it becomes unstable and starts tearing itself apart. The limit sits somewhere between 320,000 and 400,000 solar luminosities depending on which model you trust. Stephenson 218 was exceeding it by a lot. The radius estimate, based on the star's luminosity, temperature and distance, came out to roughly 2,150 times the radius of the Sun. Not 1,700 like the early estimates for UY Scuti, not 1,420 like VY Canis Majoris, 2,150. If that number is correct, and the best available data suggests it is, Stephenson 218 is the largest star we have ever confirmed. The radius of 2,150 solar radii translates to about 1.5 billion kilometers. That's a billion with a B. The distance from the Sun to Jupiter is about 778 million kilometers. The distance from the Sun to Saturn is about 1.4 billion kilometers. If you placed Stephenson 218 where the Sun is right now, the surface of the star would extend past the orbit of Saturn. Some estimates, depending on how you account for the extended atmosphere, push the surface even farther out, possibly reaching the orbit of Uranus or even Neptune. That's not a star sitting in a solar system, that's a star replacing the solar system. The volume is incomprehensible. If you could hollow out Stephenson 218 and fill it with suns, you would need more than 10 billion of them before you ran out of space. 10 billion. That's more than twice the number of people currently alive on Earth. That's roughly twice the age of the universe in years. That's a number so large that trying to visualize it is not just difficult, it's pointless. You can write it down, you can say it out loud, but your brain will refuse to process it as anything other than an abstraction. 10 billion suns inside one star. The mass of Stephenson 218 is estimated at somewhere between 30 and 50 solar masses, though the exact number is uncertain. That might sound contradictory. How can a star weigh only 30 to 50 times as much as the Sun, but be 2,150 times larger? The answer, once again, is density. The outer layers of Stephenson 218 are so diffuse that they barely qualify as matter. The density is lower than the vacuum inside a laboratory chamber. The star is not a solid object. It's not even a gas in the way we normally think of gases. It's a region of space where hydrogen and helium atoms are drifting outward from a central core, held together by gravity but just barely. The core itself is where the mass is concentrated, a dense, hot region where fusion is happening, surrounded by an enormous bloated envelope that contributes almost nothing to the total weight but dominates the total volume. The surface temperature of Stephenson 218 sits around 3,200 Kelvin. That's cooler than the surface of the Sun by nearly a factor of 2. It's cooler than Antares. It's cooler than VY Canis Majoris. It's one of the coolest stellar surfaces we've ever measured. That cool temperature is why the star glows red, and it's why so much of the star's energy is radiated in the infrared rather than the visible spectrum. If you looked at Stephenson 218 with human eyes from a safe distance, you would see a dim, deep red glow, so faint that you might miss it entirely if you weren't specifically looking for it. If you looked at it with an infrared camera, it would dominate the field of view, a blazing sphere of thermal radiation pumping out nearly 500,000 times the energy of the Sun. The spectral classification is M6, which places Stephenson 218 among the coolest and most evolved red supergiants known. M6 stars are rare. Most red supergiants sit somewhere between M0 and M4. An M6 classification suggests the star has cooled and expanded to an extreme degree, pushing right up against the limits of what stellar physics allows. Some astronomers classify Stephenson 218 as a red hypergiant, a designation reserved for the most massive, most luminous, most unstable stars in the galaxy. Others prefer to call it an extreme red supergiant. The distinction is not trivial. Hypergiants are a separate class of object, and the criteria for what qualifies as a hypergiant are not universally agreed upon. But by any reasonable definition, Stephenson 218 is at the extreme end of the spectrum. It's not just big, it's as big as a star can get before the physics breaks down completely. The distance to Stephenson 218 is roughly 20,000 light-years, or about 6,000 parsecs. That's a long way. The light reaching our telescopes tonight left the star around the time humans were just starting to figure out agriculture. The distance estimate comes from multiple lines of evidence, including the cluster's radial velocity, its position in the galaxy, and the reddening of the starlight caused by interstellar dust along the line of sight. The uncertainty in the distance is still significant, probably plus or minus a few thousand light-years, which translates directly into uncertainty in the star's size and luminosity. But even accounting for the error bars, Stephenson 218 is enormous. If the distance is on the low end of the estimate, the star is slightly smaller than 2,150 solar radii. If the distance is on the high end, it's even larger. Either way, it's the biggest thing we've confirmed. The fact that we nearly missed it is worth pausing on. Stephenson 218 is not a faint star. It's radiating nearly 500,000 times the energy of the Sun, but it's also 20,000 light-years away, sitting behind thick clouds of interstellar dust that absorb most of the visible light before it reaches Earth. In optical wavelengths, the star is almost invisible. Early surveys of the region using visible light telescopes either missed it entirely or catalogued it as a faint red dot, too dim and too obscured to warrant follow-up observations. It wasn't until astronomers started systematically surveying the galaxy in infrared that the star showed up clearly. And even then, it took years of analysis to realize what they were looking at. The initial classification was messy. The star's position in the cluster was slightly off from the main concentration of members, sitting on the outskirts in a region called the Stephenson 2 Southwest group. Its brightness was unusually high. Its proper motion, The tiny drift in the star's position on the sky, caused by its movement through space, didn't quite match the other cluster members. For a while, some astronomers thought Stephenson 218 might not be part of the cluster at all. Maybe it was a foreground or background star that just happened to be in the same line of sight. Maybe it was an unrelated red supergiant sitting at a completely different distance. The debate was eventually settled by more detailed proper motion studies and spectroscopic analysis that confirmed the star's radial velocity matched the cluster. Stephenson 218 is a member. It's part of the same population of massive stars that formed together millions of years ago in a single burst of star formation. The slightly off-center position is probably just the result of the cluster slowly dispersing over time, with some members drifting outward from the core. Open clusters are not tightly bound. They're loose associations of stars that will eventually spread out and merge into the general stellar population of the galaxy. Stephenson 2 is already in the process of dispersing, and Stephenson 218 is one of the stars that has drifted slightly away from the center, but it's still part of the family. The techniques used to confirm the star's size are the same techniques astronomers use for all distant supergiants. You measure the angular diameter, the apparent size of the star's disk on the sky. You measure the distance. You combine the two to calculate the physical radius. The angular diameter measurement comes from infrared interferometry, or, more commonly, from modeling the star's spectral energy distribution, the way its brightness changes across different wavelengths. If you know the temperature and the total luminosity, you can calculate the surface area required to produce that much light, and from the surface area you can derive the radius. The distance comes from the cluster's properties, its radial velocity, and the reddening caused by interstellar dust. Every measurement has uncertainty, every calculation has assumptions, but the different methods tend to agree within the error bars, which gives astronomers confidence that the numbers are at least in the right ballpark. The instruments that made this possible include the 2-micron all-sky survey, or 2-MASS, which mapped the entire sky in near-infrared wavelengths, and the Spitzer Space Telescope, which provided detailed infrared photometry and spectroscopy for thousands of stars in the galactic plane. Without those surveys, Stephenson 218 would still be sitting in the data as an unidentified infrared source, too faint invisible light to attract attention. The systematic nature of modern astronomy, the practice of surveying the entire sky in multiple wavelengths and cataloguing every detectable object, is what allowed astronomers to find stars like this. You don't find them by luck. You find them by looking everywhere and measuring everything. The implications of a star like Stephenson 218 are profound and uncomfortable. Stars are not supposed to get this large. The theoretical models of stellar evolution, the equations that describe how stars form, how they burn fuel, how they die, all of them predict that there's an upper limit to how big a star can grow before it becomes unstable. That limit is set by a balance between gravity pulling inward and radiation pressure pushing outward. The more massive a star is, the more energy it generates in its core, and the stronger the radiation pressure becomes. At some point, the radiation pressure becomes so strong that it blows away the outer layers of the star faster than gravity can hold them down. The star starts losing mass through powerful stellar winds, shedding material into space at a rate that can strip away several solar masses per million years. This mass loss limits how large a star can grow. Once the luminosity exceeds a certain threshold, the star can't hold itself together anymore. It either explodes or collapses, or loses so much mass that it shrinks back down below the limit. Stephenson 218 is sitting above that limit. Its luminosity of 440,000 solar luminosities exceeds the Humphreys-Davidson limit by tens of thousands of solar luminosities. It shouldn't be stable. It shouldn't be holding itself together. And yet there it is, glowing steadily in the heart of Stephenson 2, radiating energy at a rate that should, by all rights, be tearing it apart. The fact that it exists suggests that either our models are missing something, or the star is in a brief, transitional phase that won't last much longer. Astronomers sometimes call stars like this ticking time bombs. They're not stable. They're not in equilibrium. They're in the process of self-destructing, and the only question is how much longer they have before the structure fails completely. The most likely scenario is that Stephenson 218 is in the final stages of its life, possibly fusing carbon or oxygen in its core, possibly even heavier elements like neon or magnesium. Each stage of fusion happens faster than the one before, and each stage releases less energy. The star is running out of fuel. The core is contracting. The outer layers are expanding in response, growing larger and cooler as the star climbs toward the end of its evolutionary track. At some point, probably within the next few 100,000 years, the core will fill with iron, fusion will stop, and gravity will win. The core will collapse in less than a second, rebounding in a supernova explosion that will briefly outshine the entire galaxy. The explosion will scatter the heavy elements forged in the star's core across thousands of light years, enriching the surrounding gas with carbon, oxygen, silicon, iron, and every other element heavier than helium. That enriched gas will eventually collapse under its own gravity, forming the next generation of stars and planets. Some of those planets might develop atmospheres. Some of those atmospheres might support life, and the atoms in the bodies of whatever life forms evolve there will trace their origin back to the explosion of Stephenson 218, a star that existed for a few million years in the early 21st century, glowing faintly red in a cluster 20,000 light-years from Earth. The discovery of Stephenson 218 is a reminder that the universe is still full of surprises. For decades, astronomers thought VY Canis Majoris was the largest star. Then UY Scuti took the title. Then better measurements revised UY Scuti's size, and the title was up for grabs again. And then someone took a closer look at the stars in Stephenson 2, ran the numbers, and realized that one of them was bigger than anything we'd ever seen. The fact that the star exists at all is extraordinary. The fact that we found it is even more so. It was sitting there the whole time, glowing steadily in infrared, hidden behind dust and distance, waiting for someone to point the right instrument at the right patch of sky and realize what they were looking at. But here's the uncomfortable part. Stephenson 218 is the largest star we've confirmed. Not the largest star that exists, the largest star we've confirmed. There's a difference. The galaxy contains somewhere between 100 billion and 400 billion stars, depending on how you count. We've measured a few million of them in enough detail to calculate their sizes. Most stars are small, dim red dwarfs that barely register in surveys. A tiny fraction are massive, luminous supergiants or hypergiants, and an even tinier fraction are extreme objects like Stephenson 218, sitting at the edge of what stellar physics allows. We've surveyed the sky systematically. We've catalogued millions of objects, but we haven't looked everywhere. We haven't measured everything. There are regions of the galaxy so heavily obscured by dust that even infrared surveys can't penetrate them. There are distant clusters we haven't studied in detail. There are faint infrared sources sitting in the data right now, catalogued but not analyzed, waiting for someone to take a closer look. It's entirely possible, maybe even likely, that somewhere out there, buried in the galactic plane behind thick clouds of molecular gas, there's a star even larger than Stephenson 218. A star we haven't found yet. A star that's sitting in a catalogue right now as an unidentified infrared blob, too distant or too obscured to measure accurately with current instruments. And one day someone will point a better telescope at it, run the numbers and realize they're looking at something bigger than anything we've ever seen, and the title will change hands again. That's how this works. The largest star is not a permanent designation. It's a provisional claim, subject to revision every time the instruments improve or someone takes a closer look at an object we thought we understood. For now, Stephenson 218 holds the crown, 2,150 times the radius of the Sun, 10 billion times the volume, radiating 440,000 times more energy than the star that makes life on Earth possible. Sitting 20,000 light-years away in a massive cluster of red supergiants, glowing faintly red in the infrared, ticking down the clock toward an explosion that will scatter its guts across a significant fraction of the galactic disk, the largest star we've ever measured, the most extreme object of its kind, and probably, not the largest star that actually exists. Just the largest one we've managed to find so far. The horizon of cosmic scale, what lies beyond. But here's the uncomfortable part. Stephenson 218 is the largest star we've confirmed, not the largest star that exists. The largest star we've confirmed. There's a difference. The galaxy contains somewhere between 100 billion and 400 billion stars, depending on how you count. We've measured a few million of them in enough detail to calculate their sizes. Most stars are small, dim red dwarfs that barely register in surveys. A tiny fraction are massive, luminous supergiants or hypergiants, and an even tinier fraction are extreme objects like Stephenson 218, sitting at the edge of what stellar physics allows. We've surveyed the sky systematically, we've catalogued millions of objects, but we haven't looked everywhere, we haven't measured everything. There are regions of the galaxy so heavily obscured by dust that even infrared surveys can't penetrate them. There are distant clusters we haven't studied in detail. There are faint infrared sources sitting in the data right now, catalogued but not analyzed, waiting for someone to take a closer look. So let's take a step back. Let's line them up and see what we've actually found. 5 stars, each one a cosmic behemoth, each one representing a different chapter in the story of how big a star can get before the universe says no. The Sun, for reference, has a radius of about 432,000 miles. That's the baseline, the thing we orbit, the thing that makes life on Earth possible, the thing that, by every human standard, is enormous. Now multiply that by 1,420 and you get VY Canis Majoris, the former king, the star that held the record for more than a decade before better measurements knocked it down a peg. 1,420 times the radius of the Sun translates to roughly 987 million kilometers across the diameter. Place it where the Sun is, and its surface extends past Mars, possibly reaching Jupiter. Light takes 6 hours to cross it. The star weighs about 17 times as much as the Sun, but has lost so much mass through stellar winds that it's shedding 30 Earths worth of material every year. It's radiating somewhere between 250,000 and 500,000 times the luminosity of the Sun, depending on which study you trust and how much of the infrared excess you attribute to dust versus the star itself. VY Canis Majoris sits about 3,900 light-years from Earth in the constellation Canis Major, glowing faintly red, pulsating on an irregular schedule, dying loudly and slowly and visibly. It was the champion. Then the measurements improved, the distance estimates shifted, and the radius came down from the early figures of 1,800 or 2,000 solar radii to something closer to 1,420, still enormous. Still one of the largest stars known. but no longer the largest. Move up the scale and you hit RW Cephei, an orange hypergiant sitting somewhere around 1,500 times the radius of the Sun. Orange hypergiants are rare. They represent a brief transitional phase between red supergiants and blue supergiants, or possibly the other way around, depending on which evolutionary track the star is following. The spectrum is unstable. The luminosity fluctuates. The whole structure is teetering on the edge of something catastrophic, either a supernova or a complete collapse into a black hole without the usual fireworks. RW Cephei is close enough and bright enough that we can study it in some detail, but the measurements are messy. The star is losing mass. The outer atmosphere is thick and irregular. The pulsations are chaotic. Pinning down a single number for the radius is like trying to measure the size of a cloud. You can estimate, you can model, but the answer changes depending on where you draw the boundary. The best current estimate sits around 1,500 solar radii, give or take a few hundred depending on which layer of the atmosphere you're measuring. Place it where the Sun is and Saturn is inside the star. Light takes about 7 hours to cross the diameter. The star is a hypernova candidate, meaning when it finally explodes, it might release 10 to 100 times more energy than a typical supernova, or it might just collapse directly into a black hole and disappear without a flash. Nobody knows. The physics at this scale is speculative. Next up is HD 269551, a red supergiant in the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way about 160,000 light-years away. HD 269551 has a radius estimated at roughly 1,439 times the Sun, which translates to about 1 billion kilometers. That's right at the threshold where you start running out of solar system to fill. The orbit of Saturn sits at about 4 billion kilometers from the Sun. HD 269551 would swallow Saturn if the two objects were placed side by side. The star is heavily obscured by dust, both in the surrounding interstellar medium and in the thick shell of gas it's been shedding for thousands of years. It's unstable. It's pulsating. It's a supernova candidate, expected to explode sometime in the next few 100,000 years. The fact that it's in the Large Magellanic Cloud rather than the Milky Way makes it harder to measure, but the distance to the LMC is well established, which reduces one source of uncertainty. The star is about 160,000 light-years away. The light we're seeing left the star around the time the first modern humans were beginning to migrate out of Africa. That explosion, if it's already happened, won't reach us for another 160,000 years. Then there's WOHG 64, another resident of the Large Magellanic Cloud, another red supergiant buried in a thick cocoon of dust and gas. WOHG 64 has a radius estimated at around 1,540 times the Sun, making it larger than VY Canis Majoris, and larger than most of the famous red supergiants in our own galaxy. The dust envelope around WOHG 64 is so thick that some astronomers initially thought they were looking at a protoplanetary disk or a binary system rather than a single star. The envelope extends outward for thousands of astronomical units, glowing faintly from the star's radiation, blocking most of the visible light and re-radiating it in the infrared. Studying WOHG 64 requires infrared telescopes powerful enough to penetrate the dust, and even then, the measurements come with enormous error bars. The star is pulsating. The radius changes over time. The mass loss rate is high enough that the star has probably shed several solar masses worth of material over the last few thousand years. It's one of the most extreme objects in the LMC, And the LMC itself is a laboratory for studying massive star evolution because the distance is known and the metallicity is different from the Milky Way. Stars in the LMC have lower abundances of heavy elements, which affects how they evolve and how large they can grow. WOG64 is what you get when you take a massive star, give it low metallicity, and let it expand to the absolute limit of what physics allows, and at the top of the heap, at least for now, sits Scuti, the star that briefly held the title of largest known object in the universe before the measurements were revised and the crown slipped away, and then, depending on which study you trust, slipped back. Scuti's radius has been estimated at anywhere from 750 to 1,943 solar radii, depending on the year, the instrument, the distance estimate, and how you account for the pulsations and the dust and the extended atmosphere. The most commonly cited figure these days is around 1,708 solar radii, though some recent analyses push it back down to around 900. The uncertainty is frustrating, but it's also unavoidable. Scuti is far away, somewhere between 5,000 and 9,500 light-years, depending on which parallax measurement you trust. It's heavily obscured, it's pulsating on a 740-day cycle. It's losing mass. The outer layers are barely bound to the core. Measuring the size of Scuti is like trying to weigh a cloud while it's evaporating. You can estimate, you can model, but the answer depends on which moment you choose to freeze the measurement. If the radius is 1,708 solar radii, Scuti is the largest. If it's closer to 900, it drops below Stephenson 2-18 and possibly below WOG64. The title keeps shifting not because the stars are changing, but because our ability to measure them is improving and the uncertainties are narrowing. What we know for certain is that Scuti is one of the largest stars in the galaxy. What we don't know for certain is whether it's the largest, and that uncertainty is going to stick around until we get better instruments and better distance estimates and a clearer understanding of where the star's photosphere actually ends and where the extended atmosphere begins. So those are the 5. Canis Majoris, RW Cephei, HD 269551, WOHG64, and Scuti. 5 stars, each one large enough to replace the solar system, each one radiating hundreds of thousands of times more energy than the sun, each one ticking down the clock toward a supernova or a hypernova or a direct collapse into a black hole. 5 examples of what happens when you take a massive star, let it burn through its fuel, and watch it expand to the absolute edge of stability. But here's the question. Is there a limit? Can stars get bigger than this, or have we already found the upper boundary? The answer, frustratingly, is both yes and no. There is a theoretical limit to how large a star can grow, and it's set by something called the Eddington limit. The Eddington limit describes the maximum luminosity a star can sustain before the outward pressure from radiation becomes stronger than the inward pull of gravity. Stars shine because they're fusing hydrogen into helium in their cores, releasing energy in the form of light and heat. That energy radiates outward, pushing against the overlying layers of gas. Gravity pulls inward, holding the star together. As long as the two forces are balanced, the star is stable. But if the luminosity gets too high, the radiation pressure overwhelms gravity and starts blowing away the outer layers. The star loses mass faster than it can replace it. The structure becomes unstable. And eventually the star either explodes or sheds so much mass that it shrinks back down below the limit. For a red supergiant, the Eddington limit sits somewhere around a few 100,000 to 1,000,000 times the luminosity of the Sun, depending on the star's mass and composition. Stars like VY Canis Majoris and Stephenson 218 are already pushing up against that limit or exceeding it. Their luminosities sit in the range of 300,000 to 500,000 solar luminosities. They're losing mass at catastrophic rates. They're pulsating, they're unstable, and they can't grow much larger without tearing themselves apart. The maximum radius for a red supergiant based on current models is probably somewhere around 1,500 to 2,000 solar radii, maybe 2,500 in the most extreme cases. Beyond that, the star simply can't hold itself together. The outer layers drift away into space, the radius shrinks, and the star either collapses or explodes before it can expand any further. But those limits are based on models that assume we understand stellar structure, stellar winds, mass loss rates, and the physics of radiation pressure in extreme environments. And we don't, not completely. Every time we find a star that shouldn't exist according to the models get revised. VY Canis Majoris shouldn't exist. Its luminosity exceeds the theoretical limit. Stephenson 218 definitely shouldn't exist. And yet there they are, glowing steadily in infrared, radiating energy at rates that should be tearing them apart, holding together for reasons we don't fully understand. The fact that they exist suggests either the models are wrong or there's some mechanism, some stabilizing effect that we haven't accounted for yet. Which brings us to the future. Are there larger stars out there waiting to be found? Almost certainly. The galaxy is enormous. We've surveyed a tiny fraction of it in enough detail to measure individual stellar radii. There are entire regions of the Milky Way so heavily obscured by dust that even the best infrared surveys can barely penetrate them. There are distant clusters like Stephenson 2, where we've only just begun cataloguing the member stars. There are objects sitting in the data right now, faint infrared blobs with catalogue numbers that nobody has bothered to analyze in detail because they're too faint or too far away or too obscured to measure accurately with current instruments. The James Webb Space Telescope is going to change that. Webb's infrared sensitivity is orders of magnitude better than anything that came before it. It can see through dust. It can resolve faint objects at enormous distances. It can measure the spectral energy distributions of individual stars in distant clusters with enough precision to calculate accurate radii and luminosities. Webb has already started finding things that don't fit the models. Galaxies that are too bright, too massive, too well-formed for their age. Black holes that shouldn't exist yet. Stars in the early universe that assembled faster than they should have. And as Webb continues its survey of the nearby galaxy, as it maps the infrared sky in unprecedented detail, it's almost inevitable that it will find stars larger than anything we've measured so far, maybe not much larger. Maybe only 10 or 20% bigger than Stephenson 218, but enough to shift the record. Enough to remind us that the universe is still full of surprises. There are also candidates already sitting in the literature. Stephenson 2DFK5, another member of the Stephenson 2 cluster, has been measured at around 910 solar radii, give or take 180. The error bars are enormous, but the upper end of the estimate pushes it above 1,000 solar radii. And if the distance to the cluster is on the high end of the range, the radius could be even larger. There are red supergiants in the Magellanic Clouds that haven't been studied in detail yet. There are hypergiants in distant spiral arms of the Milky Way that we've only just begun to catalogue. Any one of them could turn out to be larger than Scuti or Stephenson 218 once we measure them properly. And then there's the question of what's happening in other galaxies. The Milky Way is not a particularly unusual galaxy. It's a mid-sized spiral with a relatively normal population of stars. Other galaxies have different metallicities, different star formation rates, different environments. Some of them might produce stars even larger than the ones we've found in our own galaxy. The Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light-years away. We can detect individual stars in Andromeda with modern telescopes, but measuring their sizes is difficult because the distance introduces enormous uncertainty. If there's a star in Andromeda with a radius of 3,000 solar radii, we might not know it yet. The measurements are too hard, the uncertainties are too large. But as telescopes improve, as interferometry techniques get more sophisticated, we'll start resolving those objects, and the record will shift again. The philosophical impact of discovering stars like these is hard to overstate. For most of human history, the stars were points of light on a celestial sphere, unchanging and eternal. The idea that they were distant suns, each one potentially larger and more powerful than our own, didn't emerge until the last few centuries, and even then, the scale was hard to grasp. A star twice the size of the Sun was remarkable. A star 10 times the size was extraordinary. A star 1,000 times the size was almost unimaginable. And yet here we are, cataloguing stars that are 1,500, 1,700, 2,000 times the size of the Sun, stars so large that light takes most of a day to cross them, stars that could swallow entire planetary systems and still have room left over. The discovery of these objects forces a recalibration of what we think is possible. It pushes the boundaries of what the universe allows, and it reminds us, in the most visceral way possible, how small we actually are. You are standing on a planet that's 7,900 miles wide. That planet orbits a star that's 864,000 miles wide. That star is a speck of dust compared to VY Canis Majoris. VY Canis Majoris is a speck of dust compared to Stephenson 218. And Stephenson 218, for all its size, for all its luminosity, for all the energy it's pouring into space every second, is still just one star in a galaxy of hundreds of billions, a galaxy that's one of trillions. The scale is so absurd that your brain stops processing it as reality and starts treating it as abstraction, numbers on a page, words in a script. It doesn't feel real because it can't feel real. The human brain did not evolve to comprehend distances measured in billions of kilometers or luminosities measured in hundreds of thousands of suns. And yet these objects exist. Right now, as you're reading this, Stephenson 218 is glowing faintly in infrared 20,000 light-years away, radiating 440,000 times the energy of the Sun, shedding mass through stellar winds, pulsating on a timescale of years, ticking down the clock toward an explosion that will scatter its atoms across a significant fraction of the galaxy. VY Canis Majoris is doing the same thing 3,900 light-years away. GUI Scuti is pulsating in Scutum. WAAGC 64 is glowing in the Large Magellanic Cloud. RW Cephei is teetering on the edge of collapse. All of them are real, all of them are happening, and none of them care whether you can comprehend them. The enduring mystery is not whether there's a larger star out there. There probably is. The mystery is how much larger stars can get before the physics breaks completely. We've found stars at 1,420 solar radii. We've found stars at 1,708. We've found stars at 2,150. Can a star reach 3,000? Can it reach 5,000? Or is there a hard limit somewhere around 2,000 or 2,500 where the structure simply can't hold together anymore? The models say yes. The observations say maybe. And the next generation of telescopes will give us a better answer. But here's the thing. Even if we find the largest possible star, Even if we measure it down to the last kilometer and confirm that nothing larger can exist, the universe will still be full of things we haven't found yet. Larger black holes, brighter quasars, more distant galaxies, more extreme environments. The larger star is just one category, one record, one line item in a catalogue of cosmic extremes that spans everything from the smallest subatomic particles to the largest structures in the observable universe. And the catalogue keeps growing. Every telescope we build reveals new objects. Every survey we conduct finds new extremes. The universe is not running out of surprises. It's barely getting started. So yes, Stephenson 218 is the largest star we've confirmed. For now. The title will probably change hands again in the next decade or two as Webb surveys the galaxy and measures objects we couldn't resolve before. And when that happens, the articles will get updated, the videos will get remade, the record will shift. And somewhere, buried in the data from a survey that hasn't been analyzed yet, there's probably a star even larger than Stephenson 218, glowing faintly in infrared, waiting for someone to take a closer look. The universe has been patient for 13.8 billion years. It can wait a little longer. So here we are. 5 stars, 5 monuments to the absurd, each one large enough to replace the solar system, each one radiating hundreds of thousands of times more energy than the thing that makes life on Earth possible, each one ticking down the clock toward an explosion that will scatter its atoms across thousands of light years, seeding the next generation of stars and planets and possibly life. And every single one of them is temporary. Not just temporary in the sense that they'll explode in a few 100,000 years. Temporary in the sense that the title they hold, the record they represent, could slip away the moment someone points a better telescope at the right patch of sky and realizes what they're looking at. Canis Majoris was the champion, then it wasn't. Scuti took the crown. Then the measurements improved and the crown slipped. Stephenson 218 sits at the top of the list right now, 2,150 times the radius of the Sun, the largest confirmed star in the universe, and somewhere out there, buried behind dust or sitting in a catalogue as an unidentified infrared blob, there's probably something even larger, something we haven't measured yet. Something that will shift the record again and remind us that the universe is not done revealing its monsters. The Sun is enormous by human standards. It contains 86% of the mass in the solar system. It dominates everything within billions of miles. And compared to the real giants, compared to the hypergiants and the red supergiants dying loudly at the edge of stability, the Sun is a grain of sand. A dim, ordinary, middle-aged star in an unremarkable part of the galaxy. We orbit a speck of dust, and we've been measuring the mountains. The largest star is not a permanent title, it's a placeholder, a provisional claim that holds until the next survey, the next telescope, the next refinement in how we measure distance or luminosity or size, and that's the point. The universe doesn't hand out permanent records. We do, and we revise them constantly as the